Machine Learning Coffee seminar series. So we have a full program this semester as well, and we continue sessions here in Otaniemi every second week in Kumpula. So I'd like to introduce my counterpart from Kumpula side, who has been speaking in the series last year, Professor Laura Saarinen.
Hi, hope to see you all in Kumpula also.
She'll chair predominantly the sessions in Kumpula. We may need to switch every now and then. And then we have Haula El-Mekkawi, who is helping us coordinate the thing. Thanks, Haula. And also the one more contact person is Miikka Miettinen sitting over there. So if you need to reach out to people who are organizing this, they may be easier to reach than me and Laura. But anyway, let's go to the business. So that's why we are here. So we have a highly exciting speaker today, pioneering mobile robotics, who is running two companies at the moment, and I'm sure we'll hear a bit about those two. Very welcome, Jari.
Thanks. Yeah, so good morning, everybody. I'm kind of surprised to see so many faces at 9 a.m. in Otaniemi. I never actually been before 10 a.m. here. But anyway, so as mentioned, I'm Jari Saarinen. The first thing I want to say that I'm at no way a machine learning specialist. My background is in automation and robotics, and I actually started pretty much 20 years ago across the corridor in the automation system technology. And for 15 years I was, well, student researcher, senior researcher, and then became a CEO. So in fact, I've been over 5 years CEO of Team Robotics, which means that I'm pretty much no expert of anything anymore. But about the company, so in the beginning of 2000, we were, well, actually on that side of the AS building, and we had this Center of Excellence in Generic Intelligent Machines, about 50 researchers in total, both in here Otaniemi half and half in Tampere University of Technology. And around 2013, there was a lot of political changes here in the university side, and also we were about to come to the end of this Center of Excellence. And then we were looking at the world, seeing that, okay, the technology is maturing. I see a lot of talented people around me. Why not establish a company and start making business out of the research that we have conducted? And that was the beginning of Team Robotics. We had zero understanding of business, but a lot of competence in robotics. And I'd say that we are pretty much leading mobile robotics company at the moment, still growing, not super large, but let's say that we are moving in Finnish scaling to a SME status. And sort of from history, which is explained, we started to sell what we had sold before. So basically, research and development projects for other companies. And then over the years, we have worked in different domains, security, forestry, entertainment, retail, logistics, marine, and so forth. So what my presentation today is more about is not about machine learning itself. You will not learn anything about machine learning today from me. Maybe through the use cases, you get some inspiration. And to add actually into this complexity, so I was introduced as part of two companies. So 2017, we actually founded another company that is fully focusing on autonomous driving. And you might have seen some of the publicity here in Otaniemi as well. So we have had this, first we had this Renault Twizy here as sort of a bus pilot, and then later on this summer we have been running this Gotcha bus as a pilot here. Now it's going to Karamalmi, then it's going to Hämeenlinna, and so forth. So those basically how these two companies are tied up. We are operating under the same roof at the moment. We are basically developing the same technology. Sensible 4 applies this into autonomous driving, and Him Robotics is doing all sort of mobile robotics applications. About the team, this is actually the size of the Him Robotics team, so 27 engineers. Very heterogeneous. Ladies, please send CVs. We need some diversity into the team, and also it's very homogeneous in the sense that almost everybody has an automation systems technology background. Very good when you argue about things, everybody agrees, but if you want to create something new, then it's maybe not the best combination. And just shortly, what we are sort of focusing on is the automation software. So we have a lot of competence, we have a lot of background in processing, for example, 3D LiDAR data, how to make a map, how to position within that map, how to use that information to detect obstacles and predict things, and then turn this perception information into actions and run that in real time. That's also one sort of very important aspect of everything in mobile robotics, is that everything has to work in real time, otherwise it's not really that useful. So, short videos from our different technology teams, how things work mostly. So positioning or navigation is about knowing where you are, finding a way from this point to another point, and not hitting anything in between. We're using sort of special representation in the mapping, so it's probabilistic. Normal distribution transfer is the name, and then on top of that we are running or underneath we are running a graph lab, so basically optimizing a set of local nodes and motion in between, and thus finding globally consistent. Then these maps are used for positioning, so map is needed for the reference. So always when you have a machine, it needs a reference. The map is providing you that reference. It's in a similar way that in a GPS you always have the global position, but not always you can trust on the GPS, so that's why you are also using different software. And this is sort of the mapping task itself. To me, it's let's say the closest of machine learning that I have been doing. So basically, you are learning about the structure of the world. Just that in a research world, in a literature, simultaneous localization and mapping is never sort of put into the same category as machine learning itself. Let's move into the obstacle detection tool. So here the objective is then when the machine is moving to detect what's around the machine, basically to build a situational awareness. So first of all, you need to make sure that you don't collide into anything, and then if there is some moving obstacles, then you need to make sure that you are not colliding anything in the future. Here we are applying some, like, let's say, more closer to the machine learning community. So there is, well, we can draw rectangles around objects. But then when we think about different use cases, it's not always just enough to have, for example, the camera and do 2D tracking in the image and then determine that, okay, there is object moving into that direction. What you need to also consider is the different use cases or situations that are influencing the use case. So you may have darkness, you may have low visibility. And so this is about directly from 3D data calculating features. Then you have, I think this one was using just simple SVM to classify directly from the 3D point cloud the objects. And then sort of the final stage of the perception tasks before the control is to understand that where can we move within our local environment. While that might be more or less trivial if you are on a road, for example, where you have just flat surface around you, then if you go into a forest, this might be a completely different case. That you have to analyze the environment in a sense that you have to be, for example, the leader sees objects, reflections coming from a grass, which are not really obstacles for the robot itself. Also very nice machine learning task is that you just take LiDAR data and then directly from LiDAR data you try to classify the different classes that you see. So this would be, for example, in this case, our client was interested about detecting the negative obstacles, so something that you can fall into, positive, and then if there is water. Basically, in all of the tasks, whether it is positioning, obstacle detection, traversability, or whatever sensor perception task, one thing that always makes solution more robust is if you can use multiple modalities at the same time when you are performing your task. So this was an example that there was a combination of the camera data and the LiDAR data which are put into a same frame of reference, whether it is 2D the image or 3D representation. So that was a short overview, and then let's look piece by piece and maybe dig that much deeper. On the slide, all right. One thing that we are sort of aligning is the way we are developing the software. So what we are doing actually is what we call full stack automation software. So basically a software solution where you can plug in different sensors and it produces you autonomous mobility. And by aligning, we have made certain decisions like we use only 3D data in positioning, mapping, obstacle detection, and this sort of frames the development into certain streams that makes it more efficient to develop the software as so. What I would first like to address is that I have a bunch of researchers and students, is that that the input data quality and assumptions are something that greatly influences the usability of whatever you are doing. So how we, for example, see this is when you have multi-sensor systems, you have different sensors, even different sensor modalities in a different locations of a physical body. The first thing you need to do is extrinsic calibration so that you get all the data in the same frame of reference. Here is an example of plotting two different LiDAR data, and if you don't have them in the same frame of reference, then basically the two sensors, which should represent the same world, give you two different viewpoints. So that's one of the things that actually we spend quite a lot of time when we are deploying something. Would be fun to have some machine learning algorithm that you can just drive around and then suddenly you have everything in the same frame of reference. What we are actually using is motion-based optimization. So we are basically calculating the trajectory. We drive a calibration routines, and then you calculate motion for each sensor individually. And then you have an optimization algorithm that is trying to minimize the errors between the sensor motions and provide you the translations and rotations between the sensors. Second, not so mathematical, but more of an engineering task and software quality task is synchronization. Again, when you have a number of sensors, number of algorithms running in your computer, you must make sure that everything is measured in the same time. So if there is, for example, 100 millisecond synchronization error at any point in a chain of your solution, it can mean, even in like Otaniemi speeds, it can mean already like a meter error if your positioning is 100 milliseconds delayed. This probably there is a machine learning way because everything can be solved by machine learning. But how we are actually solving is sort of making our own system time and then trying to match the acquisition time as close as possible to this timestamp that we create ourselves. And data quality is something. While you're building your application with one assumption, you just might find that this assumption is not really valid on another day. So this is something that sort of we advertise as our speciality. So because we are in Finland, so the left image was San Francisco and the right image was the Finland image, and this makes us the absolute specialist in handling the data in snow conditions worldwide, globally. And actually this also is one aspect that brings a lot of interest into our company. All right, so those are sort of the boring tasks that you have to do before you can do actually the science. Then, okay, let's do this. I already explained a little bit about the localization and mapping, but first of all, the mapping. So that's about creating the frame of reference for the whole system. You have to have it in order to be able to produce a repeatable system. So automation is about repeating things. So if you have a problem which is a unique in the sense that every time it changes, then it's probably not something that you want to solve with automation. But if you have a problem which just repeats itself over and over again, then that's where you look solutions for automation. And then the positioning is basically the grounding of position with respect to the frame preference. And this is just an example from mapping with forest machine, as I explained. So we basically convert the 3D data into a set of normal distributions, which then you have a mat to do optimization so that you can align consecutive scans, and then you move on. And every time you add a scan or a local map, you start creating constraints between these motions. And these constraints are something that you can add on then, for example, GNSS information, odometry information, registration information, and one important concept is loop closing. So whenever you are incrementally building something, you are always introducing error into the system. And loop closing means that you return into a position where you have previously visited. And when you can do that, and you have this constraint that provides your current position to your previous position, that's a loop close. And then you can run an optimization that sort of optimizes the whole trajectory that you have traveled so far. So in a way, SLAM is a problem that you cannot solve with sort of one state. So pose cannot be your state. You have to have the map and the pose as a state. Right? And as I explained that this is my understanding of machine learning in my world, while it's not considered machine learning in the machine learning world, what actually is interesting is that there is a lot of value for the data as well. So this one was taken by a forest machine, and then when the forest machine is working, so that was fully manually operated work cycle. So the trees were cut by this driver and the machine was just moving there. What's interesting is the data that you can acquire then. So that you get this trajectory throughout the forest, and while integrating the data, you can then start creating, you can create classes for different trees. You can identify the tree density, diameters, the volume of tree that you have in this forest. So this is actually then the value that you can add on there, and certainly a machine learning task there. All right. Let me try. So obstacle detection and tracking, of course, for autonomous driving, the sort of the system deployment is highly dependent on this because this is the safety layer. So until we can somehow show that this is 100% reliable, or it's at least more reliable than any human or some percentile of humans, there is no way that you can just go ahead and deploy autonomous cars. So in a way, very important task which is still sort of under development, and you can find all sort of solutions almost daily in scientific papers as well. How we actually approach this, we have two layers. So one is reactive, directly take sensor data, what you see, calculate from that sensor data that do we have any immediate collision danger. If we have, then react. So this is sort of running at the sensor frequency. Then second is predictive. So what you there try to do is then identify the objects in the world that themselves can influence the state of the world in the future. So for example, a pedestrian approaching a street, you have to take into consideration that in 2 seconds this suicide candidate might be in front of you. So this is about the reactive. We actually use here lidars and radars at the moment, and we sort of have, from the controller, you have the trajectory of the car for next 2 to 3 seconds. And then within this trajectory that you know that the controller will do, you start looking at, do we have anything in front of us which causes or which can collide with us. So this is very much engineering and not so interesting. What is more interesting is then when you start classifying the objects around you. This is now combining camera data, so 2D information and LiDAR information. And again, the first thing you have to do here is the synchronization and calibration. And now we have calibrated the data so that we have in the same frame of reference, we have the both data. We use deep neural network classifier to classify the different object types. It's very, very good for that. And then we project the data of 3D LiDAR into classifications. And from that data, laser data, you get very precise position. So that's about 2 centimeter position. You can estimate the size, and then actually we are at the moment trying to also include the radar information. Radar is very bad on classifying or providing you exact position, but what it's good for is to estimate the velocity. And so we try to group these different observations into sort of a super class of features, and then you use this in the data association where you then track these different individual components. And then of course from here, the next step is that you have a model which says that you have these objects here going into these velocities or these directions, and then you can start using the time as the predictor. Planning. Planning is probably the most traditional AI task that there is. So that's textbook stuff. And then, of course, control is about executing the plan that you get from the planner. There are approaches. There are approaches, for example, NVIDIA, I think, was trying or is still trying to directly map the human driver outputs into the sensor data inputs and trying to sort of build the ultimate driver in a sense that you just get data into your network, and then you have the control commands from human, and the wish is that when you collect enough data, the car by itself magically learns how to also control it. How we do is a bit more mathematically, so we calculate free space, so we know where the car can go, and then we detect the obstacles, and we have an example here, not the best video, but anyway, you calculate the objects, and then when you know where it's free, you know where the obstacles are, then you just do a replanning. And control itself is, well, it is sort of state of the art, but it's a model predictive controller then that is taking a number of future or piece of trajectory to the future and then calculating optimal control that follows. Yes. And then just a few videos of the use cases where everything works magically. or will work, and this is sort of also the mission statement of GIM now that we are looking at the site. So this is a video from the Gacha Otaniemi pilot. Looks so nice and peaceful, but I can tell you that there is thousands of hours of headache, sweat, endless nights to get this running. One of the key visions for Sensible 4 is to be able to create a new way of mobility. We are looking at, let's say, this campus area is a good example. There is a mass transportation hub, like a metro station. And then you have people working around here, so there is an everyday need for mobility in this area. There are people living here, and how we want to bring this system is so that it's going to be part of the mobility as a service one day. Maybe in 10 years, when we step out of the metro, the basic assumption for us is that there is a bus waiting for me. I can just step in and it takes me exactly where I commanded it to go. Second part, good life. This is quite a prototype level, let's say, product yet, but it's an internal product development as well. And where we are aiming with this one is then to have an assistive device for visually impaired. And this is run in close collaboration with blind union or association, and this Teuvo here is blind himself. He's been using all his life a guide dog, and he's very keen on sort of part of the research team in a way that all the user experiments at the moment are done by him. But anyways, all the tech that I showed is there, so what you need to do is you need to detect that do we have obstacles where a person can fall into, do we have obstacles that are high, so they are hitting into, and then you need this navigation function where we calculate the free space, detect the curves, and then you have a waypoint navigation which then guides this person to a place where he wants to go. We initially had a different video for that, but didn't got the permission to show. But efficient industry is of course something that we are looking into. This is sort of interesting from the machine learning perspective that here we are, as GIM Robotics, we are providing the mobility, so the autonomous navigation function. And then we have a partner who is developing the machine learning part. And for example, in retailing, you have different inventory tasks that can be made more efficient. You have basically, well, it's inventory, but here the example was that this system was monitoring continuously the different categories of items, and if they started to run out, then you alarm that, okay, this needs to fill in. And actually the bread was a use case here because it's something that is on the fresh side, so you also have a fast turnaround. Endless possibilities. I'm done with the presentation. Happy to discuss.
Thanks a lot for the talk. Maybe I'll ask the first question is, are you taking into account somehow what the humans that the robots encounter are planning to do? Or you just consider them as objects who can move with a certain speed in an arbitrary direction?
Presently, we are not considering behavior-based planning, or how to say it. Or it's intention planning or something like that. It's not that least yet. So this is something that probably, for example, for the guide robot, we need to take into consideration somehow. So that, for example, on a busy walkway, you wouldn't want the guide to go like that, but more like assume that this guy will do something, and then if that assumption is wrong, then just go wrong. There is some, I know there is some research on this topic, but I've never really seen any real practical applications.
My question is more on the financial aspects of the robotics. The Boston Dynamics, which is for the non-expert users, just like me, is the crown jewel of robotics industry, hasn't been able to make any money during these decades or something like that. It's just over from one company to another company. So, is it the same scenario? It's more like a research company, and they're negative turnover always. Is it the same situation with your company, or is it the trend in the whole robotic? It's more than industrial, and it's just research, and you're just burning cash to come up with cool ideas.
Yeah, this comes down to the user need and your solution. If you think about the Boston Dynamic business, what's the need that they've been solving? One is to produce cool hydraulic systems that walk. And this turned into a product development for military. So, okay, our robot could maybe walk in a terrain that tracked rover cannot, which is not really true actually. This was cut down because, well, if you have a big dock, either you have to have a truckload of batteries, or then you have this jet engine, which then tells every enemy you have within 10 miles that where you are. So then that was moved. Then they started to focus more into that, okay, what could we do on a consumer side? And started to develop a smaller, electric, and maybe it does that. But what is the need that this robot is solving? If I would take a consumer robotics company, I would take iRobot, one of the most established, oldest robotics companies there is. There is a clear need. I need my bloody floor cleaned every day. Let's make a robot for that. And then you are selling those. And the same, from my perspective, we've been operating all the time in a business to business. So we have not really focused on consumer robotics. Actually, the guide dog is the first attempt, but even that has a special flavor. So the cost structure of our solution is still such that there's only a handful of people who you would get so interested that they would afford to buy it. So in this guide robot, there is actually a business model which is based on a current business model, and that is sort of that the dogs themselves are leased. So the government is paying for the users, or the actual government is paying the dog for the users. So in this way, you can calculate that the cost of the system can be get back in lifetime of the product.
Can you give some information about the computing infrastructure, for robots? Could you integrate distributed computing and then communication between the robots and the platform? Everything is done inside the robot?
No. It really depends depends on the use case. But let's say that the standard industrial solution is that you have a central point which is doing then the coordination if you have multiple robots. So for example, every AGV system has just an interface that the robot itself is like so stupid. It gets a command that move from this point 2 meters ahead, and then it moves. And if it doesn't get a continuation from there, then it just waits for the headmaster to say something. So this is sort of the way that these systems are built today. You don't just push them into a factory and then they start operating something. And it's sort of natural because, for example, logistics, it always depends on what's happening in that system in general. So you have to have a warehouse management that generates the tasks that, okay, now we have a pallet ready here, make a pickup task and deliver a task.
So for the most advanced robots in your company, how much machine learning done inside robots and how much done in the data center?
We don't really do any machine learning.
And for all kind of processing, like object detection and vision and
all that. So everything that you need to run real time, all that has to run within the robot. There is no communication infrastructure that would support reliable enough communication that you could run any critical algorithm outside of that.
even the one in the manufacturing, you have some demonstration where your robot runs inside a factory, even inside a factory, cannot rely on data center.
No, not really.
Okay.
So everything that is in a closed loop, I would say that runs on the robot. The infrastructure within the robot, you can have a distributed. So you can use several computers to fulfill that. But to transfer wirelessly, the key word here is wirelessly, data somewhere, compute a decision or observation or something, getting it back, and then use it to close the loop. It's sort of, there's just, as I mentioned, synchronization. And here comes the latency, which you cannot really predict how much it is.
Do you have experience with simulations, like simulations for developing?
A little bit.
There's a big discussion about this, like how accurate it is and if you can transfer the model.
I'd say that we haven't done any transfer learning tasks yet. We actually just took one open source simulator, which is producing you this realistic camera data, and then we're working on it right now, but we don't have any like data. It's more for us, it's a tool for system level testing. So you can tune your control algorithm, use the simulator to see that, okay, is my controller still stable? Does the system do what it's supposed to do? But we haven't really used it in a way that you have in mind that you use the data and you get the annotation from the simulation and then you transfer this back to your vehicle, get it outside and see what it does actually.
Yeah. Not for that level.
Not that level, no.
Do you see that as a progression?
Possibly, I don't deny anything, everything is possible.
Yeah, thanks. I think we are running out of time slowly. So
yeah.
Many thanks.
Onko
for
sieltä
the
vielä hyvä kauan?